you see the derive screen. Now what we're going to do is we're going to see how to author and manipulate matrices. It's very easy. I hit A for author, and I author the expression, okay? Now to author matrix, I put a bracket there. I'm going to put a few spaces so hopefully you can see what's going on there. Then I'm going to put my 0.8, comma, 0.1. Okay, now I'm going to put a comma there. Okay, that 0.8.1 in brackets is the first row. Then I'm going to put my 0.2, comma, 0.9 in brackets. Then I'll give a couple spaces. The spaces aren't necessary. I'm just putting them there so you can see a little more clearly what I'm doing. But we see that we have two row vectors inside of a encompassing set of braces, and we get this matrix. Okay, and hopefully you can read that. It's just the matrix 0.8, 0.1, 0.2, 0.9. 0.8.1 in the first row, 0.2.9 in the second. Now, I'm going to author another expression that says A, I'm going to use a capital A, but derive has its own opinion of whether this should be a capital or not. So it doesn't really matter whether I use a capital or not. Derive is going to do what it wants to do. But then I put a colon equals. Okay, that's A colon equals. And then I'll hit F3 to bring that matrix, the highlighted matrix, down. And what I get is the expression here. Now it's highlighted, and I'm going to move the highlight up because I think you might be able to see that better. It just says A colon equals 0.8, 0.1, 0.2, 0.9. Now, if I want to multiply that matrix by, let's say, a column vector, I put the column vector 600, 400 into the author line. Let's spread that out a little bit so you can see it real clearly. Hopefully you can see this clearly. Okay, so there we have the matrix times the 600, 400. And I put that little backwards apostrophe on there. It's over to the extreme left of the number line at the top of the keyboard. It's right next to the 1, just to the left of the 1, and above the tab key. Now, that really doesn't do anything. What that should do is that should convert the 600, 400 to a column vector. And it just doesn't do that, and it's supposed to, I think. It certainly should, whether it's supposed to or not, but for some reason it's not doing that. Anyhow, that's what it looks like. Now, if I simplify that, it gives me the vector 52480. That should be a column vector. Derive doesn't seem to want to understand column vectors, but it should be in a column like we've written it. Okay, so that's how we do that multiplication. And it wouldn't matter if I had the backward apostrophe on there or not, the way derive seems to work. One of the few things I really don't like much about derive is that it confuses this issue of rows and columns. Now, I could have done the same thing by coming down to the author line and just authoring A times the vector 600, 400. Now I'm going to put the backwards apostrophe on there because it's supposed to be there, but it doesn't make any difference. And then I simplify that expression, and we see what we've got below the highlight. A times 600, 400 transposed is 52480. In other words, this expression here is the same as this. We got the bottom expression from this calculation and the top from this calculation. So A really does stand for this matrix. Now, if I author the expression A squared, Okay, just using the caret to do a squared. So we see that we've now got a squared. And simplify that. Well, we get a fraction which we better approximate. And the approximated fraction is just our 0.66, 0.17, 0.34, 0.83. That's our a squared. That's our two-year transition matrix that we just saw. Now, if we author the expression, let's say a cubed, I can approximate that, and I get my three-year transition matrix. I can author the following. I can do vector, parentheses, and now I'm going to say a to the n for n going from 1 to 10. If I approximate that vector, it gives me a whole list of matrices. Now the list is too long to see. If I want to see my population vectors, I'll just bring this expression down and I'll move my cursor over. Hopefully you can see that. I'm going to do an times 600, 400 transpose. And I can approximate that. And that will give me a whole list of populations. 520, 480, 464, 536, and so forth. These are going to be the population figures. And what we have, what we have coming up, I had to check the next page there because I wasn't sure whether they're going by 1 or by 10. But what we have looks something very much like this. And we'll see where this comes, or how we use this in just a minute. Now let me just author another expression. A to the 100th times 600, 400. And approximate that, we see that we get 333 1/3, 666 2/3. And of course that's familiar to us as the limit of what we get, 333 1/3, 666 1/3, if we do an infinite number of transitions. We also could note a couple of other approximations, but I'll leave those to you.